Welcome to Khetz and in this video I'll be talking about stationary points and points of inflection. Okay, so let's see, where do we start? Let's start with stationary points. So now we've been talking about the derivative, we're talking about gradients and stuff like that. You now know how, I assume, you now know how to find the gradient given a function. So it's the rate of change, or the gradient can be seen to be the rate of change. As from straight lines, probably know that you delta x delta y, which is the change in y, divided by the change in x, okay? And you can kind of draw some sort of triangle to show that you know what you're doing, I guess. So that is how you basically look at this in a way, and it can be increasing just like it is in this case, and it can be decreasing. And there is a surprisingly large amount of people who don't quite know how to tell whether a function is increasing or decreasing. Like in words, they basically can look at it, but they can't basically explain it in words. So let me try to do that, or let me try to explain that before we get into the content. So let's say you have a function, some sort of function, doesn't matter what it is. Maybe it looks something like that. Now, how would you quantify whether this thing is increasing or decreasing? Well, for such a function, certain parts are increasing and some parts are decreasing. Is that the case? And the answer is no. Now, if you look at this thing, as you increase your x values, so let's see what happens. So you always look at your function as a function of x if you have your xy plane. So now, as you increase your x values, which means as you go to the right, what happens to the y values? That should be your question. Now, if you look at this, you start off with a low y value, somewhere down there. And now, as you increase your x values, you'd see that it basically, well, for that point, it basically goes down. But for most part, let's only look at, let's exclude this part and only talk about this section, right? So in this yellow section that I now want to focus on, as we increase our, starting maybe at that point, as we increase our x values, the y values also increase. So let's see how you can actually write that. So for increasing function, when you increase your x values, your y values increase. And for a decreasing function, when you increase your x values, your y values decrease, right? And in terms of straight lines, you can look at it like this. So we'd say that such a straight line is increasing because as we increase our x values, the y values are also increasing. But this straight line is decreasing because as we increase our x values, the y values actually go down. So that is the basic summary of what is going on in terms of increasing and decreasing. And we will use this terminology quite a lot. And it's good that I basically start with such a thing. Now back to the gradient. The gradient is basically the rate of change. And if you use the derivative, you're finding the instantaneous rate of change, which is basically the change at a particular point of a graph, right? And now we know that it can be increasing or decreasing, but what if you find that the derivative gives you a value of 0? What is a gradient of 0? Or how would you show that this is a gradient of 0? Let's say you have a gradient of 2, it can be something like that, it's basically positive. Let's say you have a gradient of -2, it can be something like that, so it's negative. But what about a gradient of 0? What happens at that point? So that is basically a level plane or a straight line in the horizontal way. And this is basically level ground. There is no change as this is change. So a gradient is change or a slope. So there is a slope here. If you're standing here, you basically look at it in that sense. If you're standing here, you're basically going downhill. But if you're here, you're basically on level ground. So this is a gradient of 0. This corresponds to a gradient of 0. And at such a point, we usually have, or we basically have something that we call stationary points. So for a parabola, if you find the gradient at the turning point, you should get 0. right? And that is your stationary point. That is your stationary point, and that is the basic definition of what a stationary point is. You basically have no change at that point. You basically have level ground, and you expect your derivative to be 0, right? And now that we know that, what happens in the other places, or what happens when we find the gradient, or when you find the derivative, the other part of the function? Well, you can try to do that, and one example I can use is the function of x squared. So by now I do expect that you know the basic behavior of the function x squared. So it should look something like this. It should pass through the origin, or it should have the turning point at the origin. So now our function is f of x equals to x squared. Now if we find the derivative of that, it's basically 2x. So you can see that if you substitute negative values of x, you're going to get a negative gradient, or you're going to get a negative value for your gradient, basically. But now if you substitute positive values, which will be on this side, then you basically expect to get a positive gradient on this side. But at this specific point, which is 0, if you substitute 0, you're going to get 0. And that is where you have your turning point. That is where you have your turning point, and this is your stationary point. So basically, a stationary point is just a point where you have a derivative of 0. That is basically how you'd go about doing that. Now, we can also use this derivative thing to find whether a function is increasing or decreasing. So once again, if you find the derivative, it's just this. Now, we did mention that if you substitute negative values, you get negative value for your gradient, which means that on this side it's decreasing. So to summarize that, if your first derivative is less than 0 or is negative, then your function is decreasing. And if your first derivative is greater than 0, then your function basically is increasing. And when you find the derivative to be 0, the first derivative, you basically have a stationary point. So I guess that is all that we can talk about, at least for now, with regards to stationary points. Let's move on to something else. And it is related to what we have been talking about. So everything in this video is related in a way. We're now going to talk about concavity. And now we can say that concavity is related to the shape of a function. So if a function looks up, like something like this, it's basically concave up. And if a function looks down, or it basically frowns, then it basically is concave down. But it's not always clear cut, or you can't always tell just from looking at a function whether it's concave up or concave down. What I just drew now, they're basically parabolas. It's basically easy to see for a parabola because there isn't any funny behavior with parabolas. You just have something which either looks up or down. So that's something to take away, that for parabolas, it's easy to see whether it's concave up or concave down. But once again, in the previous example, in the previous case, we talked about the stationary point, and it divides part of your graph where you have negative or you have a decreasing function, and part of your graph where you have an increasing function. And it can be the other way around. That is perfectly fine, because if you have such a function, your stationary point should divide your positive side to your negative side. So it doesn't matter which one comes first, but at that middle point, or at that turning point, you have a change from a decreasing to an increasing, or from an increasing to a decreasing function. Now with concavity, we now are going to talk about a change in concavity, right? So first of all, how do we find whether something is concave up or down, right? So we're going to talk about how we find that, and we're going to talk about this change in concavity. So for the first derivative, we talk about stationary points, but for the second derivative, we talk about points of inflection. So if you have a function, let's say you have a function like this, and at some point it changes. Let's say this is concave down until this point, and this is concave up. right? So let's just write up and down. So let's say this is concave down on this side, and on this side you have concave up. This point where you have a change in concavity is your point of inflection. And the way that you'd actually find this point is by using the second derivative test. So let's talk about that test that we basically use to sum up concavity as well as the point of inflection. So this is how you'd basically do it. And before I go to that, here's another definition of concavity, which is much more mathematical, if I can put it that way. If we say that something is concave up, if you draw, so it's basically concave up or concave down between 2 points, or between an interval, or in an interval, or between some set of points, right? In a particular state or in a particular part of the function, not the whole function. It might happen that it's basically concave up for the whole function, but in most cases, or in some cases, you might find that it's not. So let's talk about a section from A to B. We say that this function is concave up in this section if you can draw tangents to the graph which are below the graph. So any way that you draw tangents, as you can see, all your tangents should be below the graph, and this is when you have this as concave up. So you have your tangents below graph, or you have your graph above the tangents. Now, in the opposite direction, if you have something like this, and you have your tangents above your graph, or you have the graph basically below the tangents, and this is where you have something which is concave down. So you can look at this with respect to your tangents. If all your tangents between a certain interval are basically above or below, that's how you tell whether something is concave up or concave down. So this is a more involved method. So you basically have to check if all of your tangents are above or below, and we'd rather not get into that, but it's good that you know how to define that in terms of tangents. And now I'm going to move on to the second derivative test, so to sum up everything, points of inflection and concavity basically. So now we are talking about the second derivative. And you find the second derivative by basically finding the derivative of an already existing derivative. So you have an original function. You're going to differentiate that original function to find your first derivative. Then you're going to differentiate this derivative to find another derivative. And you can go on as long as, I don't know, right? You can go on and on and on, but here's where we're stopping, where we have f double prime. That is how you pronounce it. So we're now talking about the second derivative test, and it says, or there are quite a few points to basically talk about. So in grade 12, you can assume that if you have f double prime of x equals to 0, then you do have a point of inflection, right? But that is not always the case, because you can have a point which is a okay. So in grade 12, you can assume that once you find a stationary point, so you find a stationary point at some point by finding the first derivative equals to 0. Now you can say that if you have the second derivative at that same point as 0 as well, then you do have a point of inflection. But this is not always the case. You might find that there is no change in concavity. So the point of inflection indicates a change in concavity, but it happens that you might find that a point which is a stationary point and which basically has a point of inflection, which basically has a second derivative of 0, is not a point of inflection, but for grade 12, this is perfectly fine. Once you have concluded that a point is a stationary point and you find that the second derivative at that exact same point is 0 as well, then you can say that that point is a point of inflection. Now, if you find that, so the first condition, so everything falls under this condition. So if f prime of c, where c is just a point, and f double prime of c. So if the second derivative is less than 0, then you basically have a local maximum somewhere in your graph, and I will expand on all of these definitions in a bit. And if you have your second derivative as positive, then it means that you basically have a local minimum at this point. So you have a local minimum. And now if you have the second derivative as 0, then you have a point of inflection. This is for grade 12. You can immediately conclude that it's a point of inflection. There are other tests that you have to do to be absolutely sure that you indeed have a point of inflection, but this is enough. So the first part of this thing, or the first part of the test, is you have to be sure that at that point you have a stationary point. And once you have that stationary point, then you will have a change in concavity. You will have a point of inflection if you have this. Now, I don't think this makes a lot of sense at this point, right? So I just want to just break it down and have a graphical explanation of all of this, or basically just to show what is happening. And I will start with just the point of inflection by itself, and then expand to talk about just about everything that I talked about in this video, just so it makes more sense. So I'm now editing the video, and I just realized that I haven't really talked about how this stuff actually relates to concavity. So I only talked about the point of inflection, and I will talk more about that at a later stage. So basically, if you look at a local maximum, so you basically expect the maximum where you have everything else below it, right? So if you have a graph which is concave down, which basically looks like, let's say, for example, a parabola which is pointing downwards, then that is where you have a maximum. So whenever you have a maximum, then you expect your graph to be basically concave down. Now, when you have a minimum, your graph actually points up, or it actually smiles. You can look at it like a smile, so it actually is up. And that is where you'd have your graph as concave up. So this is how you'd interpret this stuff, and you'll see that as we go to the graphical approach of this video. So starting with the point of inflection, if we talk about a graphical approach to looking at this, let's say you have some sort of graph over there, and it looks like this. So at some point there, P, you have a point of inflection if you have a change in concavity from concave down to concave up, or from concave up to concave down, or something like that. So let's say at some point there you have some change. You have a point of inflection if you have a change in concavity. So this is, you can say this is concave up until that point, and then on this side you have something which is concave down. So once you have a change in concavity, this is the most important thing, change in concavity. This is the most important thing. When we talk about points of inflection, we are talking about changes in concavity, and not just a change in whether something is increasing or decreasing, right? So that is the graphical way that you can analyze a point of inflection. Now, to summarize just about everything that we talked about in this video, I'm now going to draw something which looks like a third order curve, or a third degree polynomial. And now I'm just going to talk about how this maps to all the other things. So let's say this is the highest power of this function is 3, and we have some other coefficients. It doesn't matter. You can have 3x squared plus something, it doesn't matter what we have on this side. I just want to focus on the highest power, this highest power. It doesn't matter what you have following that. We can even only talk about this because it's enough to have that. It's a third order polynomial. We can draw a third order curve from that, right? And now if you differentiate this thing, f prime of x, you should get 3x squared. And this is a parabola. You should know that by now. So it should look something like this. It is positive, so it should look something like that. This is a parabola that we do expect to look like that. And if you go a step further to kind of, so let me just try to align these things. Let me try to align. I'm getting to something here, so I just want to make sure that the stuff is aligned. Is it? It's not. Let me do this. Let me do it this way. And I'm going to draw a line. Then I'm going to have that parabola. Not the best, but I hope that the point comes across. Okay, something like that. Let's say it crosses at that point and that point. And this is where we are right now, after differentiating this original graph, which is this one. And then if we differentiate again, let's differentiate this thing again. If we do that, then we basically get the second derivative, and it should be 6x. And this should be familiar to you. It's just a straight line. So how would you view a straight line? A straight line should be, it's positive, so it should be something like this. It should look something like this. It being positive should tell you that it should go up in that direction, right? And we have a point of intersection somewhere there. Okay, now let's talk about this and relate this to all of the concepts that we've been talking about. Remember that when you do your second derivative test, now if you find that you have a positive second derivative at a point, then you have a local maximum. So at that point, you'd have a local maximum. This is what it means. And then we call it a local maximum because if you look at all the other points around it, this is the highest point, right? So it's not, you can find that this local maximum is not the ultimate highest point of the whole graph. And that is why we'd rather call it a local maximum, right? So with respect to its neighbors, if you want to call it that, so with respect to the neighbors or with respect to the points which are found immediately next to it, it is the highest, but it might not be the highest for the whole function. And the same applies for this point, right? So at this point, you have a local minimum because with respect to the neighboring points, it's basically the lowest point. It might not necessarily be the lowest point of the whole graph. So that is what we have over there. And let's just say that at some point, maybe here, we have a point of inflection. So at some point there, we have a point of inflection. And the point of inflection is a change in concavity. Don't forget that. So let's say this side is concave down until that point, and then this side is concave up, right? So from the point of inflection to this side, it's concave up, and from the point of inflection to that side, it's basically concave down. And these points are actually related to their derivatives, and here's how they're related. So at that local maximum, you basically have some sort of x-intercept in your derivative. And the same applies for a minimum. You basically have an x-intercept for that minimum point that you have over there. And here's why this works out. If you have a double derivative or the second derivative and you basically find it as positive, then you have a local maximum. And if you find it as negative, you have a local minimum. And now if we work our way up to this first derivative, let's only talk about this first derivative, or let's talk about this type of function. How would you find these points? You basically set your function to 0. And this function is just a parabola. If you set that to 0, you should get your x-intercepts, right? But what are these x-intercepts? These are basically points on your graph where you have this gradient as 0. You should know that at a maximum or minimum, the gradient should be 0. So at these points, you have f prime of x equals to 0. At this point, you have f prime of x equals to 0. So the gradient, this means that the gradient of your original function, which is this one, at these points is 0 because these are some sort of turning points, or these are maximum points. You have no change in gradient at that point. And this is how these things basically relate. So you can take those points as being f prime of x equals to 0, both of them, right? And because we're moving from that to that, this is a second order thing and it's a parabola, you expect it to behave just like that. Now the point of inflection is basically the midpoint of these 2 points. So if you have f prime of x equals to 0, if you have both of these points, you can now find the midpoint of them to find the turning point. So the turning point of the first derivative should be your point of inflection of your original function. That is how this maps up, or this maps out. You basically can trace that to that point. And this same point of inflection can be mapped to the x-intercept of a straight line, which would be your second derivative. Remember that we said that the second derivative, if it's equals to 0, then we basically have a point of inflection. Once we've identified a stationary point, of course. And now this turning point is a turning point, just like the local maximum or the local minimum, it is a turning point. So what is the gradient at that point? We already know that at that point as well, we basically have a gradient of 0. Once we have a gradient of 0, that tells us that we are at this point. And in terms of a straight line, just like with any other function, if this is the x-axis at f of x equals to 0, we have that. So this would be a point of inflection as well. So this is how all of this maps up. Once you derive something, you basically, or once you differentiate something, you're basically decreasing its power, as you can see. So from x cubed, you decrease the power to x squared, and then finally to x with the power of 1. And moving from such a thing to a parabola to that, I basically explained how you interpret all of that stuff, or how the stuff is basically related. So I hope this video was quite useful. I hope you got some value from the video, and you can use all of these concepts to your advantage or to whatever application that you have in front of you. And if you have any comments, just leave your comments in the comment box, send me an email, talk to me, and yeah, just let me know your thoughts, any comments, anything, just about anything. If you don't understand anything as well, you can contact me or leave a comment. And if you haven't subscribed, please subscribe. If you like the video, just give it a thumbs up, and I will see you in the next video.